from yesterday looking at our tax rate, financial literacy activity. That should be done and submitted. Now we're going to transition back to looking at probability. Homework Module 5, Lesson 5, or knock out that additional Imagine Math to be mentioned as a Imagine Math All-Star in the future and to grow in your math abilities, which is our overall goal here. And just make sure you're keeping up with your tracker so you're completing the correct assignments throughout the week. Today we're going to look at analyzing outcomes within statistics and probability. So today you guys are going to be able to differentiate between theoretical and experimental probability and use these probabilities in order to make accurate predictions. You're going to have another quizzes today. Your goal, remember, is always 80% or higher within those 3 attempts that relates directly to today's lesson. Just a quick look once again at what is probability. We've seen this slide every lesson so far in Module 5. Remember, we're talking about the likelihood of something to happen. It doesn't mean we're getting an exact accurate measure, but it's allowing us to make a reasonable estimation or guess. Now, I want you guys to think critically about this problem. All right? Keith is awarded a penalty shot. In hockey, when you are awarded a penalty shot, it's basically you one-on-one with the goalie. And let me show you what that looks like. Just a very short clip of some of the best shootout goals in recent memory. You guys have YouTube. You can look that up if you want to watch a longer compilation of some of those shootout goals. But let's think about this. Keith is awarded a penalty shot. So he will either score a goal or not score a goal. My question is, are both outcomes equally likely? Explain. So I want you to take about maybe 5 seconds, maybe 10 seconds, and think about that question. What I'll tell you is in professional hockey, they're not equally likely. A goalie is actually way more likely to stop a shootout goal than is a skater to score. Now, some of the best people at shootouts are around like 30%, 40%. You may get a few above 50, but that's really rare. So it is more likely actually for a goalie to stop a shot in the NHL than it is for the player on the breakaway to score or the penalty shot to score. With that said, there are a lot of factors here, right? If you put me, for instance, who cannot ice skate, in the goal, the likelihood a professional skater is going to score on me is way more likely than I'm going to block the shot. So there's a skill factor that plays into this as well. So this is a difficult conversation, or this question asks you to think critically because there's multiple factors. Although there's only 2 outcomes, right? He's going to score, he's not going to score. Whether or not those are equally likely often depends on the skills of the goalie and the skills of the skater. Now we're going to transition over to another video.
How does experimental probability compare to theoretical probability? Think about this question during the lesson. Talia and Yoshi plan for 1 out of 8, or 12.5%, of the players winning a prize. During the school fair, they kept track of the numbers of total players and winners, and they recorded the data in the table shown here. How does the actual number of winners compare to the expected number of winners? The first step is to determine the relative frequency of winners during each time period. The relative frequency is the ratio of the number of times an event occurs to the total number of trials. In this case, it is equal to the ratio of the number of winners to the total number of players. We can find the relative frequency for each time period and for the total number of contestants. The relative frequency from 10 to noon is about 10 3/10%. The relative frequency from noon to 2 is about 13 7/10%. So the relative frequency for the entire day will be between 10 3/10 and 13 7/10. For the total number of contestants, the relative frequency is 58 over 475, or about 12 2/10%. The relative frequency of an event can also be called experimental probability. Which value is greater in this situation? The experimental probability or the theoretical probability?
Select your answer.
If you recall at the very beginning of this video, or yesterday, or now by looking at this spinner, the win spaces, which are the red ones, there are 2 of those out of 16. That simplifies to 1/8. So the theoretical probability of winning, meaning landing on one of these 2 red spaces, is 1/8. That is 12.5% if we take that into a percentage. So in theory, 1 out of every 8 should win, which is 12.5%, or 12 5/10%. The relative frequency, or when they conducted an experiment, meaning they actually did an experiment, they did something, right? The relative frequency ended up being 12 2/10%, which is a little bit lower than what in theory should happen based on the spinner.
The experimental probability of winning the game is 12 2/10%. This is slightly lower than the theoretical probability, which is 1/8, or 12 1/2%. The game had 58 winners out of 475 players. There were slightly fewer winners than Talia and Yoshi expected. Now you know how experimental probability is similar to and different from theoretical probability.
And with that said, we're going to go back to the lesson and explain this in further detail. So let's look at this problem now. We're going to continue with what was laid out in the groundwork based on the original problem that was in the video. So during the second day of the school fair, Talia and Yoshi recorded 43 winners out of 324 players. How does the actual number of winners compare to the expected number of winners? All right, well, we know that 1 out of every 8 people should win, which is based on theory, right? It doesn't mean we're doing anything wrong with the experiment. It's just in theory, based on the probability presented in this spinner, 12.5% should win, 1 out of every 8. Now, what happened was 43 out of 324 won. What I'm doing currently with my calculator, I am dividing. The reason I'm dividing is that's going to take it to a decimal, and you can easily change decimals to percents by multiplying it by 100, which moves the decimal 2 places over. So when I type that into a calculator and divide it, I get approximately this number. I round it. So as a percent, you just multiply by 100, right? So you move the decimal over 2, and it's approximately 13, and I'm going to bump that up, and 3/10%. Remember, 5 and above, give it a shove. So how does the actual number of winners compare to the expected number of winners? More winners won on day 2 than were expected based on the theoretical probability. That does not mean there was any form of cheating in the spin, in the game. Because more people won doesn't mean it was rigged. Theoretical probability is simply an estimate of what should, quote unquote, happen based on what's there. All right? Experimental probability is what actually ends up happening. Okay? Now, in general, the more trials you do, so for instance, the more time we would spin this spinner and the more people would participate, you're going to get closer to this theoretical probability. That's just like a rule of thumb. The more trials you get, the more accurate you tend to get to the theory. Is that once again true 100% of the time? No, but in general, if we had, 500,000 people spin this, you're going to get incrementally closer to this value over time. Okay? But more winners ended up winning here than was predicted based on the theory. I just want to note too, remember the notebook and pencil are here, so make sure you get these down. Moving on. Jaquan also kept track of players and winners for his game during the fair. Based on the results shown in the table, how many winners should he expect if 300 people play the game? So, we have no idea what the theoretical probability is here. We don't have enough information like we do here with the spinner. We are purely using this experiment that he did, the data he collected. If you collect actual data, it becomes experimental probability. And we are going to make a prediction based on this experimental or relative frequency data. All right? Well, what we know is we want to use this value. Why? Obviously, always the question. This goes back to what I just said. The more trials you get, the more accurate the prediction becomes. So because the total has the most number of trials, the most number of players, you're going to use this bottom row. You don't want to use the top row because you'll get a prediction, but because this only counts for 174 people, it's going to be less accurate. All right? The more people you deal with, the more times that game is played, the more accurate representation. All right, so let's think about this. We know 71, and there's a few ways to do this. 71 out of 416 people played. I'm going to look at this as a proportion. All right, remember, this is the winners, this is the total number of players. Well, the question's asking if 300 people play. So we don't care about 416, we care about 300. And we want to know how many would win out of 300. So we have set up a proportion here. What you can do is cross multiply. So I can do 71 times 300 equals 416x. All right, 71 times 300 is 21,300. And this is still obviously 416x, which means then I would divide both sides by 416. And that gets me a value of approximately so what does that mean? That means Jaquan should expect about 51 winners if 300 people play his game. Now, let's think if that's reasonable. Well, there were 71 winners for 416, so I know it should be less than that. And I also saw in general there's 242 and there's about 43 winners, so this should be higher than that. It should sit somewhere between 43 and 71, which it does. Okay? Another way to look at this is, and I'm just going to scroll down here, what we can do is we have this value. What this value is telling me is no matter how many people play, about 17 and 1/10% will win. So all I need to do is take 17 and 1/10% of the total number of players. So what I can do is I can take, and I'm writing it as a decimal, and I can multiply it by the number of players. Because remember, 17 and 1/10% is not 17 and 1/10. It means 17 and 1/10 over 100, which is this decimal. So I can multiply those two, and that gets a value of 51 and 3/10. Now, why are these a little bit different? Because this is an estimation. So just like this is an estimation, this is an estimation, but notice that they are very, very close. And with this, we're making predictions. And these are almost identical values here, okay? Either strategy proportion or just understanding you can multiply that percent times the total number of trials, which in this case are players, that works as well. All right, let's look at this. And this is asking you to think critically. It's not really asking us to solve anything. Amir and Marvin each flip a coin 50 times and record the results of each flip. Now, if they both flip the same coin 50 times, I want you to think how many heads there should be and how many tails should there be. Hopefully you're thinking both of them should have 25-25, right? Should be a 50-50 split. Now, the table, they conducted an experiment, so the table shows their actual results. The theoretical probability would be 25 and 25 to get a probability of 50%. Why are the results different from the expected results based on theoretical probability? The reason is theoretical probability is simply an estimate based on the probability given, okay? Or based on the information. Let me say that, given, okay? In theory, right? Theory means what should happen. So in theory, what should happen is it should be 25 and 25. But the theory is not always true, okay? Theory is rarely 100% accurate, okay? What we have here is Amir is almost dead on with that 50-50 split, right? Marvin's a little further off. That does not mean one of them flipped the coin incorrectly. I want that to be clear. They did it perfectly well. Let's assume it. It's just they're a little off from what theory states. To get more accurate, over time, the more they flip that coin, maybe they flip it 100 times, then 200, 1,000. The more times they flip the coin, the closer they're going to get to that 50-50 split. But theoretical probability is an estimate based on what should happen. The experiment doesn't always match that, okay? Rarely does it match it perfectly. Maybe you flip a coin twice and you happen to get heads and then tails, and then voila, it matches. But that's rare, okay? And that's the major difference between experiment and theory. Theory is what should happen. Experiment is what does happen once you actually conduct an experiment, once you actually do something. And here we just have a definition of experimental probability. You can pause and look through this. I don't want to read it to you because you guys have the ability to do that on your own. This Khan Academy video was posted on Monday's lesson. I'm also going to post it today on Wednesday's lesson. Please use it, particularly if you're struggling to differentiate between experimental and theoretical probabilities. Your goal for today is you're going to complete today's quizzes on analyzing outcomes. Same kind of steps as usual. Use your resources, your notes, this video, Khan Academy, Knowledge on the Go videos, the internet, me, Miss Smiles, Mr. Cardarella. Reach out whoever you need to make sure you are successful. You have 3 attempts. Use them if you do not get 80% or higher the first time. And same kind of deal, just like I said, reach out for help as needed. And just the last reminder, these are the office hour schedules as of now. If there's any changes, we will be sure to let you guys know.